Hello, good morning. So today I'm going to introduce a new topic. So far we have talked about probability of an event. Now we will talk about conditional probability. That is, given some information, we are talking about the probability of an event. So when you talk about probability of any event B or A, that is called unconditional probability. And given some information, when we are trying to assign some probability regarding the event A, then we call it conditional probability. So for instance, like I roll a dice, what is the chance of getting an even number? That is half, right? Because half of the outcomes are um, even and half of the outcomes are odd. Now if I tell you that given what is the chance of getting 6 on the upturn phase, given the upturn phase is an even number, and then that would be different from asking the probability of getting a 6 on the upturn phase of a dice. So if I apply the assumption that all the heads are equally likely, then the chance of getting 6 or any number is 1 over 6, because there are 6 faces. But if I am given the additional information that the upturn phase is an even number, then obviously there are 3 possibilities, 2, 4 and 6. Then 1, 3 and 5, there is no reason for me to consider. So out of these 3, one of them is 6, so I could say 1 over 3. So that should be the natural way of computing probability, that is restricting to the outcomes which satisfy the conditions which we know, which are within the given condition. So conditional probability is at times much more useful than unconditional probability, because we have some information, based on that we are trying to predict something, predict the chance of occurrence of an event. So therefore let us get into the formal definition of conditional probability. So we are assuming that there is an event B with positive probability. This is important. Unless B has a positive probability, we don't condition on B. If B has probability 0, then there is not much, B is not much useful information. So probability of it is read as A given B. So the this slash is read as given A given B is defined as probability of A intersection B by probability of B. Therefore, probability of A intersection B can also be written as probability of B into probability of A given B, provided probability of B is 0. That is also called chain rule. I will come to that later. And so conditional probability of A given B is a function again on the same sample space. So conditional probability I am defining as a function. This dot will denotes that here the argument will be a set from a subset of S or a event in this collection. So what we have to verify first, that this function will satisfy the 3 axioms. So first of all, P A given B is a non-negative number, so that is axiom 1. Second, now I leave it as an exercise. Verify. So this will be axiom 2. How? Because in the numerator it will be S intersection B. B is a subset of S. So S intersection B is B. So it will be probability of B over B, that is 1. And now we have got a sequence of disjoint sets. Then also you can verify that this will be the sum of A given Bn. So how? That I am leaving as an exercise. So just as a hint, then write this in the form of this definition. This in the numerator you will get union of A intersection B. Now basic set theory knowledge in set theory will tell you that union of n intersection B is same as union of n intersection B's. Now since n's are disjoint, therefore n intersection with anything will also be disjoint. That is, AI intersection B and AJ intersection B will be disjoint. So you can apply the third axiom to the union in the numerator, and then you can get the result. So I have just given you the brief outline. I hope you can write down the proof formally. So what we can show is that this is equal to, let me write the answer here. এইটো লিখা না যাব। This is the problem. Probability of A n intersection B. A n intersection B. So that's it. So this is axiom 3. Axiom 3. So these are things. This requires some work that I have outlined. You please try writing it down. Now verify that the conditional probability satisfies. So that is that is an exercise. That means now what is the result of this exercise? As a consequence, we will no longer get this directly properties of probability, since a function p defined in this way, given b is defined this way, satisfies the three axioms. So it is a probability on the same space, so it will have all the properties of probability. So p phi given b is 0, that you don't need to prove anymore. Probability of a complement given b is 1 minus probability of b, and a and c are two disjoint sets. Given probability of b, then it is additive in the same way. And if a is a subset of d, b has positive probability, then probably the monotonic property is also satisfied. So all this, in some books you see they go on to prove all this, but this is not needed. Just verify these three axioms, then the moment you verify these axioms, any function that satisfies these axioms on this collection will have automatically have these properties, because these properties follow from the three axioms only. So therefore we immediately have these results. Please have these results in your mind very carefully. So maybe I will introduce a line here. Properties of conditional probability. Properties of conditional probability. Probability proof not readed, because you have verified the three axioms. There are two ways. You go on proving each from the definition, or you just verify the three axioms and you are done. So I think that the above approach is lot smarter, that you once and for all just verify the three axioms. You get not only these properties, even the continuity theorem. Okay, continuity theorem I have not discussed with you. So there are many other advanced properties of probability function that will hold good for conditional probability. Now I am leaving a question for you to think: is it same or not? Probably suppose b is a then will this hold or not? Where I must write, where I am writing probability of b is positive between 0 and 1. Between 0 and 1. So now why I am saying 0 and 1? Because probability of b complement will be 1 minus probability of b. So probability of b is 1. Then I cannot condition on b complement. So both probability b and b complement has to be positive. So in other words, probability of b has to be proper fraction. So in that case, both a probability of a given b complement and probability of a given b are defined. Now in the question is, will this relation hold? So I hope you have enjoyed this, and please think over this question and think over the verifying the third axiom. Okay, thank you.